Last episode turned a fistful of logits into one label, positive or negative, a single decision, and then it's gone. But those same hidden states the model computed on the way to that label, they're far too useful to throw away. Today we keep them. We take the rich internal representation a transformer builds for a piece of text, squeeze it down to one fixed length vector, and hold on to it. That vector is called an embedding, and once you have one per sentence, you can do something a classifier never could. You can compare sentences directly by geometry with nothing but a dot product. Here's the shift in one picture. A classifier reads a sentence and collapses everything into a label. All that nuance flattened into a single chip. An embedding model reads the same sentence and hands you back a long list of numbers, 384 of them in the model we'll use, same transformer machinery underneath, different exit door, one throws the representation away, the other keeps it, and that kept vector becomes a coordinate you can place on a map. Why a vector and not a label? Because vectors live in a space, and space has distance. Two sentences that mean almost the same thing end up close together. Two that mean different things end up far apart. The model was trained so that a cat sat on the mat and a kitten rested on the rug land as near neighbors even though they share barely a word. Meaning becomes location. That single idea, text as coordinates, is what powers search, clustering, recommendation, and the retrieval half of every RAG system you've ever heard of. The library that makes this a one-liner is sentence transformers. Plain transformers give you one vector per token, a whole grid of them, one row per word piece. That's not what we want. We want one vector for the whole sentence. Sentence transformers wraps the model with a pooling step that averages those token vectors into a single sentence vector, and it's fine-tuned end-to-end so that average actually means something. You call dot encode, you get back one clean row per sentence. Done. Our workhorse is all Minilam L6v2, 6 transformer layers, embeddings of dimension 384, and small enough to run on a laptop CPU in milliseconds. It is the single most downloaded sentence model on the hub for a reason. It's fast, it's tiny, and the quality is shockingly good for the size. When people say, just throw it at Minilam, this is the model they mean. We load it by name, exactly like every other model in this course. Now how do we measure close? Not with straight line distance, with the angle between two vectors. Cosine similarity ignores how long a vector is and asks only which direction it points. Point the same way, you get a number near 1. Point at right angles, you get 0. Point opposite, -1. For text embeddings, this is the metric of choice because what we care about is direction of meaning, not magnitude. A short sentence and a long one about the same topic still point the same way. And here's the trick that makes cosine almost free to compute. If you normalize every vector to length 1 first, cosine similarity is just the dot product. No division, no square roots at compare time. One matrix multiply gives you every pairwise score at once. Encode will normalize for us with a single flag. So the whole similarity matrix is one clean line. The embeddings times their own transpose. We'll test it on 4 words: cat, kitten, car, and automobile. 2 pairs of near synonyms from 2 unrelated worlds. If embeddings really capture meaning, cat and kitten should light up, car and automobile should light up, and the cross pairs, cat and car, kitten and automobile, should stay dark. That's the whole experiment. A 4x4 grid where the meaning shows up as brightness. And we never told the model a single thing about cats or cars. It learned it all from how words keep company. It's one file, 11embeddings.py, and it fits on 2 pages. Page 1 loads the model and encodes our 4 sentences into normalized vectors. Page 2 computes the full similarity matrix, prints the 3 headline pairs, and saves the heat map. No training, no GPU, no dataset download, just load and code compare. Up top, the imports and the data. We pulled sentence transformer from sentence transformers plus numpy for the matrix math and matplotlib to draw the figure. Then the 4 sentences as a plain Python list in a fixed order: cat, kitten, car, automobile, because that order is exactly how the rows and columns of our matrix will line up. Keeping the order pinned here is what makes the printed pairs and the drawn grid agree. Next, we load the model and encode. One line names all mini LM L6 V2. Sentence transformers fetches it from the hub the first time and caches it after. Then a single encode call does all the work. It tokenizes every sentence, runs the 6 transformer layers, mean pools each one down to a 384 dimensional vector, and because we pass normalize embeddings, true, scales each one to unit length on the way out. We get back an array of shape 4 by 384, 4 sentences, each a point on the unit sphere. Page 2 is the comparison. Because the vectors are already unit length, the entire cosine similarity matrix is one line. The embedding array times its own transpose. That gives a 4 by 4 matrix where entry ij is the cosine between sentence I and sentence j, once down the diagonal and every interesting pair of it. We round it for printing, and we're holding the exact numbers the heat map will show. Then we pull the 3 headline scores by index and print them in that clean one-line summary: cat versus kitten, car versus automobile, and the telling cross pair cat versus car. 2 bright synonym scores up near 0.8, 1 dark cross score down near 0.1, all on a single line you can read at a glance. That printed line is the result. The heat map is just the same numbers made visible. Last, we draw and save. We hand the matrix to imshow, label both axes with the 4 words, write each cell's value into the grid in black text, and save it out as a PNG. The bright diagonal and the 2 bright synonym cells pop in yellow. The crosspairs stay dark. And that's the lesson in one square. Meaning became geometry. We just scored whole sentences against each other, but plenty of jobs need finer grain than that. Next time we zoom all the way in and label individual tokens, tagging the people, places, and organizations inside a sentence one word at a time with named entity recognition.